This video we have a gas that's gonna flow in this pipe from left to right. The speed, the entry speed V2 here in this cross-section area A2 is unknown, and it tells that the cross-section area here on the left side is 0.07 meters square, and it tells us that the density of the gas of the fluid here is 1.3 kilograms per meters cube. In the cross-section here in the narrow part of the pipe is given to us as 0.05 meters square. And it tells us that the difference in pressure from P2 to P1 is 120 Pascal. So keep in mind, as the cross-section area is big, V goes down, V for speed, and if V goes down, pressure goes up, and vice versa. If the speed goes up, then the pressure goes down. But it tells us that the pressure difference here is 120 Pascal. All right. So part A wants us to find the speed of the gas and the larger cross-section area. So here's A2 on the left side, and then here's A2 on the right side as well. So whichever V2 you want to find doesn't really matter. Okay. Part B wants to find the volume flow rate, Q, of the gas. So let's go ahead and crack out part A. So to do part A, you would just start with Bernoulli's function here, Bernoulli's equation. But here, as you keep in mind, I'm going to go ahead and set my zero reference point. So for this particular problem, keep in mind that we reference the center of the pipe. So here's my zero line, and I'm just going to draw a line that goes and touches the center of the pipe. Here's my initial height, and likewise where it goes from wide to narrow, here's the height as well. So as you can see, the height here is the same because it touches from the reference 0 to the center of the pipe. So H1 and H2 is 0. Okay, so keep that in mind. Unlike these types of problem where it goes from low to high, this problem that I have here just goes from left to right in the same height. So because of that, I'm just gonna go ahead and cross row GH1 out because H1 in this case is the same as H2. Okay, so understand when to cross row GH out, understand when not to. This one I can because the starting height at the cross-section area A2 is the same height as the cross-section area A1 according to the diagram. Alright, other than that, a key piece of information here on the problem is that the difference in the pressure from left to right is P2 minus P1 is 120 Pascal. So we need to keep that in mind. So to go ahead and find part A, to find V2, I'm just going to go ahead and simplify this. The left side, I want to keep 1/2 rho V1 square, except I'm going to move P1 to the right side. I'm moving it because the problem gives us P2 minus P1, which is 120 Pascal, right? So by moving P1 to the right side, I can say that P2 minus P1 plus 1/2 rho V2 square remains. But because I can move P1 to the right side of the function, I have P1 minus P2, which is essentially given to us as 120 Pascal. So these are little tricks you just have to pick up as you practice these types of problems, okay? Alright, so from that, I'm just going to go ahead and substitute out P2 minus P1 for what it is, which is 120 Pascal. On the left side, nothing has changed. On the right side, I carry down the 1/2 rho V2 square. So here, we are going to have to solve for V2. To solve for V2, I don't know what V1 is, so therefore I need to figure out what V1 is. I want to substitute in density for this problem. Keep in mind you cannot cancel rho out because rho is in this term, but it's not in the 120 Pascal, but it's in this one. So keep in mind for you to cancel rho out, it has to appear in every single term. It only appears 2 out of 3 terms, so make sure you don't cancel variables out illegally. Okay, so make sure your algebra is on point here. So the 1/2 I carry down. The density of this particular gas, whatever it is 1.3 kilogram per meters cube, which is given. V1 square is carried down. 120 likewise, and then likewise on the right side. The only difference here is I substituted out density for 1.3, which is the given value. I kept V2 square as a variable as well. But focus on what you're trying to find, right? You're trying to find V2. So in order to find V2, the only thing that's holding you back here is V1 or V1 square. All right, V1 is your unknown. We just have to figure that out and square that term. So I'm just going to go ahead and highlight this for you. So I simplify 1/2 times 1.3, which is 0.65. And then likewise on the right side, the 1/2 times 1.3 is just 0.65, just to clean up a little bit here. But still, we're stuck with V1. Well, how do you know what the velocity is or the speed is when it goes through this narrow pipe? Well, the continuity equation tells you that if you know the area, then you can find it, right? Well, the area for these two cross sections given, A2 and the problem tells us that it's 0.07 meters square. It also tells us that the cross section of the narrow pipe A1 here is 0.05 meters square. So I know A1, I know A2. I'm trying to keep V2 so I can solve for V1. So by solving for V1, I can substitute it out. So in this particular case, I can start with the continuity equation. I say for V1 by dividing both sides by A1. So that's why A1 is in the denominator on the right side now. I know A2, I know A1. So really, I can just simplify this really quick, okay? So A1 is 0.07, A2 is 0.07, A1 is 0.05, which are given values to us. V2 here are unknown. So as you can see now, I can rewrite V1 in terms of V2. So 0.07 divided by 0.05 will give us 1.4. The meter square units here will naturally cancel out. So V1 is indeed 1.4 times faster than V2, which makes sense because, well, as the gas here goes through a narrow section of the pipe, it will speed up and drop the pressure, okay? Now that we know what V1 is, we can just substitute in for the left side here. Keep in mind, we are trying to solve for V2, so this is one quick way to get rid of V1. So I'm just going to carry my work over. So I'm just going to state this again. I'm going to get substitute out for V1. V1 as previously calculated using the continuity equation is 1.4 V2. Please make sure you use parentheses when you substitute here. So this is 1.4 V2, but the whole term is being squared. The right side hasn't changed, okay? So here, I'm just going to go ahead and distribute this. So if you do this correctly, if you do 1.4 square times 0.65, you'll get 1.274, and V2 is being squared, so that's why this V2 square term gets carried down. The right side hasn't changed. So as you can see, the left side has a V2 square, the right side has a V2 square, and that is our only unknown here in this particular statement. So I'm just going to go ahead and do algebra, combine like terms, all that good stuff, okay? So to get V2 square on the same side, I'm just going to go ahead and subtract 0.65 V2 square from both sides. So if you do 1.274 minus 0.65 V2 square, you'll get 0.624 V2 square. Again, just a quick combined like term here. The right side, I kept 120 Pascal as is. So to get V2 squared by itself, now divide both sides by 0.624. So we'll go ahead and do that really quick. Units will naturally cancel out because Pascal is a measurement of pressure, which is newtons per area. Area in this case being meters square. Alright, so if you clean that up a little bit, 120 divided by 0.624, you'll get 192.31. And then this is V squared though. The question asks for the speed in the larger cross-section area, which is V2. So let's go ahead and square root this to get rid of the square term. And square rooting 192.31 will give you about 13.88 meters per second. So the speed in the cross section that's wider, right? The far left or the far right according to the original diagram. So if you need to rewind the video because it went from a Y to a narrow to Y. So the speed in the Y area is going to be 13.88 meters per second. That's our answer for part A. Now once you know A though, part B asks you to find the flow rate Q. So in this case, I want to use this variation of Q. Again, Q can be volume divided by time or area times speed. Here, I want to use area times speed because, well, the problem gives us area, and I just found V2, so why not, right? So area 2 is given to us as 0.07. The speed coming out of, or coming in of the Y area, or coming out of the far right Y cross-section area is 0.07. So I'm just going to plug and chug, and if you do this correctly on your calculator, you'll get 0.972. And the unit here is going to be m cubed because m squared times m is m cubed, and the unit on the bottom is second. So as you can see here, this is just essentially the same as the unit for volume over time because volume is meters cubed, and then time is in seconds. And that is it. And that is our flow rate across the wider cross-section area. Okay, I hope that helps. Stay nerdy. Don't be back.